Hello, I'm Ivar Troost, and today I'm happy to be presenting to you our latest paper, Exploring Relations in Neuroscientific Literature Using Augmented Reality, a Design Study. Our work really starts here. As more papers are published, the harder it becomes for scientists to maintain an overview. A case study. Let's say you're a neuroscientist and you want to figure out the relationship between depression, a brain disorder, and the amygdala, a brain region. In order to do that, you will need to read through a lot of papers using this document-centric workflow that a search engine would provide. You need to take a look at the abstracts, figure out where the connections are, and then make up your mind about what exactly that relationship is. And questions like how important that relationship is in the literature compared to other ones is something that is quite hard to answer. Now, you could do that manually to some extent, trying to take a look at depression in relation to a few brain regions. But the moment you try to scale that up, you start to see the problem. We need computational methods for that in order to figure out where relations are in connection to other relations between, in this case, brain regions and brain diseases. And in that way, we can better support relation exploration in neuroscientific literature, or in other words, to support distant reading, to not just read the papers themselves, but also to be able to take in the overview and better understand the whole picture of it in order to generate better hypotheses. Now, there are techniques available to do this, but they quickly start to look like this, and that is not something you want neuroscientists to have to deal with every day. We need an interface, a better interface to deal with that kind of work. And in order to integrate with the current ways of working of neuroscientists, which happens both on conventional computing devices, desktop, laptops, and also on their desk in the form of paper and books, we believe that augmented reality can play a pivotal role in trying to offer that kind of integration, while also catering to the 3D nature of a lot of elements that are part of working with anatomy of the brain. Now, there was a vision in 2019, and in 2020 we actually managed to implement a system, which I'll be presenting to you here today. What we are doing, in essence, is to take a problem space, literature exploration, and apply another solution space, that of immersive analytics. And both of these I will go into a bit more in depth in our background section. And after that, I will go through the methods that we used in order to create this prototype, talk a bit about the system design, and also how we then evaluated it, which has a particular focus on whether people would like to adopt the system in their regular workflows. If you're interested in the details of the system, I won't go too deep in this 10-minute presentation, but I very much recommend you to take a look at our walkthrough, which you can find at the link here, which you can also find in our paper. Then, what is the input of the work that we've delivered? Firstly, literature-based discovery has been pivotal in that respect, and the goal of this particular field is to exploit already known scientific knowledge to generate hitherto unknown but meaningful connections. Now, what does that mean? This way of generating hypotheses. An important aspect of that is the distributional hypothesis, and that states that if two concepts are often mentioned together in different contexts, they probably are associated one way or another. And that kind of insight can easily be harnessed through computational methods, figuring out which words co-occur in abstracts, and in that way trying to see which of these associations can be strongest. In order to enable distant reading, we also used topic model visualization. And in practice, that means that you try to use a topic model algorithm on a set of documents, in this case, diseases, then try to reduce their dimensionality to either 2 or 3 to visualize it. And where the final result shows us points in space where the distance between them relates to the semantic distance between the topics. And last but certainly not least is the field of immersive analytics, which aims to create engaging embodied analysis tools in virtual and augmented reality that try to go beyond the 2D screen paradigm. There's been some work done on toolkits in quantitative data analysis. What we really try to here do is to create generalizable concepts that allow analysis of relationships, categorical data, and text. Methods-wise, we're using a design-based research approach, working from a constructionist epistemological frame, which means that we really try to use this system as a way of thinking, moving objects in space in order to create a better mental model of it. We worked in several design cycles, of which we were presenting cycle 3A at this point, focusing on the willingness to adopt this kind of technology for practitioners. The system design, let's talk about the data that went into it, design requirements we set up, and also the design itself. For the data, we use the brain association graph, which has more than 100,000 co-occurrences of brain regions and brain diseases, including the sentences that they derived from and statistics relating to them. For example, hippocampus and Alzheimer's disease could be related, appear a certain amount of time together in the literature. And we also have the probability of when the one occurs, does the other one also occur. We also link this to other data sets, Wikidata, MESH, which is the medical subject headings, which is part of PubMed. And also we used a topic model based on LD and TSNE provided by Sunqing Huangfu, who has also gracefully helped us as part of the Link Brain Data project. The design requirements are as follows: to support open and closed discovery. So given any concept in the dataset, a user must be able to see which other concepts are related to it, to always highlight rather than completely hide elements, to enable always seeing the neighborhood and the context, to augment and not replace, so not to try to replace all the current systems that are already in place, like source management, but really try to create bridges with current devices, and then making use of the medium, not creating big global objects, but really try to think of things in terms of local objects that can be stored in a physical space. There are three main tasks that we wanted to support in this version of the system, which is to be able to inspect a concept, so ask, what is it? And get a summary, to contextualize, so to see where a single concept like depression relates to a class of items like brain regions, and for that we can use the co-occurrence statistics, and finally to also be able to explain why two things are connected, so concept to concept, where the sentences, the source sentences, and the papers relate to them can help the user explore that. So here you see the representational and visualization design, for which if you want to know the details, I'd really recommend taking a look at our walkthrough. But the big lines, you see that there are resource spheres that can be moved around by the user in space, can be slotted into widgets, which allow certain data analysis tasks to be performed, which can also be connected to data flows in order to allow filtering. Then, the evaluation. The big question we asked here is, are researchers waiting for the TAR as a serious tool in their workflow? And in order to answer that question, we use the technology acceptance model as a lens, which focuses on the perceived ease of use and usefulness, but perhaps even more so on the attitude towards using and behavioral intention to use these systems in their actual practice. We had 22 people participate in this. There's a convenience sample from diverse backgrounds, neuroscientific as well as computer scientists, and people from the social sciences and the humanities. And we conducted a video survey in order to reach a larger target audience. We had two categories of qualitative feedback. On the one hand, the aspects of the system that can be improved, color palette, finding alternative for the display of many data points. Users often found it overwhelming, and also flaws inherent to the AR platform, things we really need to take a closer look at. For example, cognitive biases in 3D cloud visualizations. Is it really worth it to do that? And also that participants rated themselves more likely to use the system if on a 2D screen, which kind of forgoes the immersive analytic aspect of it. Of course, that is hard to conclude based on the current evidence, because they have not been able to immerse themselves fully. They saw a video survey version of it, so that requires a bit more study. We also found that current work practices in the current system are not quite catered to, so there's no connection to reference managers, and that only showcases more that we need these bridges between devices in order to make this kind of a paradigm work. We also found that many people offered new directions for the system could take for future research. For example, in early tertiary education could be useful as a way to introduce the anatomy of the brain, and it might also be able to transfer this kind of way of thinking about literature to social sciences and the humanities. Now, in conclusion, we think there are real opportunities in pushing this research sphere widget data flow paradigm to its limits by expanding its scope and trying to really kick the tires on it further. And we think that the TAR as a platform can be quite powerful in speculating about the future use of AR in daily work practices. Finally, I'd like to mention my co-authors, Ghazaleh, Linda, and Wolfgang. who would love to continue discussing Datar with you and figure out perhaps how we could collaborate in the future. So thanks a lot for listening, and I hope you have a wonderful rest of the conference. Thank you.